Hey guys, welcome back. We are jumping straight into our first chapter here, evaluating expressions here in Algebra 1. So before we begin, I'd like for us to perform a few exercise warm-up problems here before jumping straight into our expressions. So for example, let's divide 12 divided by 1.5. Now here, we can consider that 1.5 is 1.5. So I'm asking how many groups of 1.5 fit into 12. But also I can move my decimal place over one place to get it back to a whole number. So for example, my divisor here will be 1.5. I'll move my decimal place over once, but I also have to do that to my dividend, which means I'll be adding a 0 here. Now I can divide 120 by 15, and that's where I get to 8, which makes sense because 8 and 4 halves will get us to 12. 8 plus 4 halves will get us to 12. All right, how about 3.3 times 7? Here we can multiply out 33 times 7 as per usual, and just be sure to move our decimal place over once. So 33 times 7, for example, 7, 14, 21, 7, 14, 21, 22, 23. But I do need to consider that we have one decimal place to the left. So instead of 231 is 23.1, because I'm multiplying 3.3, not 33, by 7. What about 11.6 minus 5.9? Let's line up the decimals. Here we'll have to regroup. We can't take 9 away from 6. So let's borrow from our neighbor. We'll take a 10 rod, 1 becomes a 0, 6 becomes a 16. We won't be able to take that 0 away either though, right? So we want to make this a 0 and this a 10. Just go ahead and do it. But 16 minus 9 is 7. 10 minus 5 is 5. That's how we get to 5.7. With a little bit of regrouping and making sure that we line up our decimals correctly. Let's try one more warm-up. Let's try a fraction problem. What if I have 10 and 2/3 minus 8 and 5/6? All right, so here I can find a common denominator. We need a common denominator for thirds and sixths. Thirds and sixths. Oh, 3 and 6 are good numbers to work with, right? 3 goes into 6. So let's go ahead and jump over to 6. We are subtracting. So I'll be sure to put that minus sign there. Now we have our common denominator, 6. So we can write 10 and 2/3 as 10 and 4/6. For example, 3 times 2 is 6 and 2 times 2 is 4. And our second will be 8 and 5/6 because this is already in sixth. All right, so we can regroup here to get 9 and 10/6. Minus 8 and 5/6. Which will get us to 1 and 5/6. Also, we can change these into improper fractions. For example, 3 times 10 is 30 plus 2 is 32. 8 times 6 is 48 plus 5 is 53. That's how we get to our improper fractions. And we still are looking at using 6 as a common denominator. 3 times 2, 2 times 32 is 64. 6 times 1, 1 times 53 is 53. Now we're at 64 minus 53. That's only 11, right? 11 sixths. Now let's go back and check. 1 and 5 sixths. 6 times 1 is 6, plus 5 is 11 over 6. It checks out. So either way. All right, now that we've had a chance to go over some warm-up problems, let's take a look at our lesson. So the question here is, how do we evaluate algebraic expressions and powers? Let's zoom in a little bit here. We're trying to answer the question for algebraic expressions. How do we evaluate them? And the answer is we're going to substitute a value for the variable and then do the operation, as we can see here in our chart. So for powers, for example, you multiply the base by itself as many times as the exponent says. So we'll be working with a few terms, like a variable, for example. This is when we start adding letters to math, alphabet letters. But this is a letter that stands for a number. Now, algebraic expressions are numbers, variables, and operations. For example, 6 plus c is an expression. Why? Because it doesn't have an equal sign. When it has an equal sign, then it becomes an equation. All right, so an algebraic expression or variable expression has numbers, variables, and operations. Like 6 addition would be plus c, or 8 subtraction would be minus x. These are expressions, not equations though. Equations have an equal sign. Now let's evaluate. Here's our first problem. Evaluate the expression when n equals 3. So we'll just simply substitute. 13 times n, for example. We'll substitute the 3. 13 times 3 to get to 39. So after substitution, here we are multiplying. Now, when a number is next to a variable, no other operation is holding them together like 13n. It's understood that they are being multiplied together. That's the understood operation. 13 can stand by itself, n can stand by itself, but together they are one term, 13n. All right, so 13 times 3. So 13n, for example, does not mean 13 plus n. Here we're multiplying 13 times 3, 13 times n. What about number 2? 9 divided by n, that's 9 divided by 3. We plug it in. 9 divided by 3 is 3. Same thing for our next one. N minus 1, plug it in. 3 minus 1 is 2. And then for D, we have n plus 8. Again, 3 plus 8 will become 11. This is called substitution. So in your class, you may have questions like evaluate the expression when y equals 2 for our simpler ones here, and we just again plug in 2. For number 1, 6 times 2 is 12. Number 2, 8 divided by 2 is 4. Number 3, 2 plus 4 is 6. Number 4, 11 minus 2 is 9. Whoops. Sorry about that. 11 minus 2 is 9. All right, let's go over to our other side. Here's our movies example. The total cost of seeing a movie at a theater can be represented by the expression A plus R, where A is the cost in dollars of admission, and R is the cost in dollars of refreshments. Suppose you pay $7.50 for admission and $7.25 for refreshments. Find the total cost. And that's $7.25 for refreshments. All right, so we're translating English into math. We're setting it up. So we have A equals 750. And R equals 725. Label that R. R is the cost in dollars of refreshments. So first I name what each variable means. A stands for admission, R stands for refreshments. And then the expression will become A plus R. So after substitution, we're going to add. This is A plus R. So now we substitute in 750 plus 725. Now we want to be careful to line up those decimal points when we're adding, right? That's the important part. Sometimes students get their decimal points misaligned. 5, 7, 14, and put that where it's supposed to go. Straight down the decimal point to get to $14.75. $14.75. Always connect the variable back to the real object in the story. In this case, we would label it dollars. Now, algebra does represent real scenarios, real case scenarios, real relationships in the real world, as our word problems show us. All right, now we're at power. What is a power? A power is an expression that represents repeated multiplication of the same factor. In 3 to the 4th power, for example, we have a base and we have an exponent. The base will be our bigger number. That's what number is going to multiply itself however many times the exponent tells it to. So in this case, it tells the 3 to multiply itself by itself 4 times. Or in other words, to take 3 as a factor and multiply it 4 times. 4 factors of 3. Now all a factor is our two numbers that multiply each other. Those are factors. So a number that's multiplying another number is a factor. So our base is 3, our exponent is 4. The 3 repeats, and it repeats 4 times. So let's go to our next section here, where we're writing out powers. So 7 to the 1st power, an exponent of 1 will always mean that the base is only used 1 time. So we just write the base itself, right? 7 to the 1st power, for example, is 7. 8 to the 1st power, 8. 9 to the 1st power, 9. Okay, B is 5 squared. Now remember, we don't usually write that exponent of 1 in A, by the way, because it's understood. Kind of like when we have a square root, which we haven't gotten to yet, we don't write the 2. It's just understood it's a square root, but there could be a cubed root or 4th root or so on. B is 5 squared, or 5 to the 2nd power. So an exponent of 2 is called squared, right? How do we read it? What does it mean? 5 to the 2nd power, or 5 squared? It means 5 times 5, or 25. All right, 5 times 5. What about 1/2 to the 3rd power? Yes, we can raise fractions exponentially. But remember, when you multiply out fractions, they're getting smaller. Why? Because our denominator is growing, right? So we'll have 1/2 times itself 3 times. Now 2 times 2 times 2 is 8, right? So we do get to a smaller number there. What about D? D is our exponent. Our variable. An exponent. Z to the 5th power. So we can use variables as bases as well. The exponent still tells us how many times that base number, whatever it represents, would repeat itself. So in other words, it's Z times Z times Z times Z times Z. 5 times. Z to the 5th power. So yes, we can think of that in variables as well, not just integers. All right, let's look at the next problem here. In example 2, suppose you go back to the theater with a friend to see an afternoon movie. You pay for both admissions. Your total cost in dollars can be represented by the expression 2A. If each admission costs $4.75, what is your total cost? All right, so we have A is $4.75. And so we're looking at 2 times a. That's our formula. Now let's substitute 4.75 for a. 4.75 times 2. Now we do want to be careful when we are multiplying out. Sometimes students will get a little confused on the decimal part, right? So 4.75 times 2, multiply it all out. But we want to go over 1, 2, bloop. Oop, that's 15, no, 14. Got it. 2 times 7, 14 plus 1 is 15. To get to 950. All right, let's take a look at 9 to the 5th power. That's number 6. 9 to the 5th power. We're practicing our powers, right? 9 times 9 times 9 times 9, 5 times. Okay, we don't have to fully evaluate that, but that's 9 to the 5th power. 9 times 9, 5 times. Now that would be a bigger number, right? If we want to add let's do our calculator here. That would be 9 times 9. 1, 2, 3, 4, 5. That's how we get to a big number pretty quickly, 59,049. What about 2 to the 8th power? That's 2 times itself, 8 times. Two times 2 times 2. All right. So we can see these numbers can jump up quickly with exponential increase. That's why when you have a virus and you spread it, it can spread so fast. For example, 2 people give it to 4 people. 4 people give it to 16 people. But then 16 people give it to 256. And then 256 people give it to a lot of people, right? That's how it can jump very fast, 65,500. That's exponential increase. Now, n to the 4th power, a variable, yes, we can multiply out the variable as well. N times n times n times n. All right, we'll return in our next video for our last example set before we jump into our exercise set. But here we are substituting and working with powers. All you do is simply take that number that the variable represents and plug it into whatever formula you're working with. And for our powers, we take that base and we multiply itself by itself however many times the exponent tells us. And we'll be working more closely with these concepts as we continue on. See you soon.